I'll be presenting a brief talk on precision manufacturing from forming presses to laser beams. So that's the theme of the day. Now, there are many words which we think we know, but we don't actually. Now, precision and accuracy are two such words which are often confused. So what is precision and what is accuracy? Often one is not clear. And today, since we are talking about precision, it's my duty to explain you the difference very clearly. When you buy any brand new equipment, any manufacturing equipment, for example, you produce number of jobs and you measure certain quality parameter and you are on the bullseye. So that means you have high accuracy and high precision. Okay, that's the ideal case. Now, after some time, what could happen in another season, maybe if there is a peak summer, you find that you are making number of jobs, but their center line has got shifted. That is, aim has got shifted, but consistency is still there. Now, that is the case for low accuracy and high precision. Okay, precision is still there, accuracy is gone. So, and the root cause for that is maybe some measuring error, some calibration is required, some orthogonality is got disturbed, some parallelism has got disturbed, some problem of sag in the scale, and so on. Okay, so can be calibrated, can be software compensated, can be mechanically corrected. Okay, so this case you can address relatively easily. But another case, after let us say 5 years of use, you may find a case that, okay, you make number of jobs, the average seem to be still on the bullseye, okay, but the scatter has increased. Okay, now this is the case of low precision but high accuracy. Accuracy is something to do with aim. So aim is correct, consistency has gone. So loss of consistency is loss of precision. And the causes for this could be mainly play, backlash, thermal variability, deflections, vibrations. And these are things which cannot be software compensated, and you have to only take recourse to reconditioning of equipment. Okay. So while loss of accuracy can be compensated, loss of precision cannot be. So accuracy is like aim, precision is to do with repeatability and stability of the process. So accuracy is depending on error, which I have said, misalignment, etc., offset, scaling error, all that can be corrected. And accuracy error can be determined, adjusted, calibrated, corrected, but precision could only be mechanically reconditioned. And then there are two types of precision. One is static precision. When you don't apply the forces, you don't do machining, you just determine the error and try to compensate it. Okay, that is called a static precision, like laser calibration in CNC machine, for example. Okay, dynamic precision is something where it is in flesh and blood, where all the forces, all the deflections, all the vibrations are there. And that is a challenge to maintain. Dynamic precision is a bigger challenge to maintain. Okay. Another definition of precision is compliance, degree of compliance with respect to what we predicted in software simulation and through CAD model, etc. What was designed versus what is actually got through the process. Okay, so that's another definition of precision, if you please. Yeah. Now, just some posers. Sorry, I am giving more questions than answers, but then, yeah, the idea is to make you think. So, suppose you want to remove 10 mm material from a job, is that easier, or removing 10 micron material uniformly from a die and mold curved surface? Which is easier? Which requires better precision? Obviously, the answer is very clear here. Okay. It is much costlier to remove 10 micron than to remove 10 millimeter. Let me tell you that. Another question, if you want to make features of very small dimension with micron accuracy on a very tiny job, is that easier, or maintaining micron tolerance on features which are widespread on a very large object, on a very large job, which requires better precision of the equipment? Now, obviously, bigger job is more difficult. Smaller, when the total job is small, it is easier relatively to maintain their interrelation. Okay. And third aspect is having a sigma level. Suppose you are in a mass production and you are talking of CPCPK or sigma level, or from an SPM. Now, from an SPM, it is better to have a precision, Or if you have a general purpose machine where you are doing variety of jobs, someday you are doing roughing, someday semi finishing, someday finishing. Okay. In a jig boring machine, you can preserve micron accuracy for long time. But if it is a general purpose machine, you are doing different things on different days, then what about the precision? So these are some posers. Of course, industry people would know the answer. But we have to see that the job has to deserve the precision from the equipment, because precision costs significant money. Okay, precision does not come cheap; it comes for a very high cost. Whenever designers are specifying tighter tolerance, they have to understand that it costs a lot more money to achieve those tolerances. So whether it is really required or it is just as per some standard, they are blindly putting some tolerance. Okay. Uh, Generally, in a big job where it is going to mate with other adjacent job, those are more critical, etc. So there more precision is required. Precision is not required everywhere. Precision is required where mating is to be there. Okay. Wherever assembly requirements dictate. Okay. Also, variability of properties and dimensions of incoming material and pre and post process must be commensurate with the process which we are referring to the precision. Okay. So one job cannot be very precise, one process cannot be precise, other cannot be very inaccurate. Okay. They have to deserve each other. So they have to be commensurate with each other, the total chain. Okay. Now, coming back to sheet forming, which this is a topic. This was a brief discussion on what is precision and what is accuracy. Uh, Generally, sheet forming is said to be the art of inaccuracy. So, I mean, it is strange that we are talking about precision for a stamping press. Okay. The simulations often are not known to match the end outcome. Okay. We are doing simulation and we find there are significant deviations when we actually do it. Because we are simulating theoretically against the CAD model, in ideal condition, we are not simulating the behavior of stamping press, the automation behavior, the behavior of dies, the large CNC machines, when they manufacture dies, what kind of distortions they will have. Okay. Other practical variables such as vibrations, deflections, overhang, gathering of wind, and hardness of active surfaces, etc. Okay. So simulation, while we are doing theoretical simulation for assuming ideal condition from formability, FEM, but we are not doing all these things which are listed over here. Of course, since the video is going to be recorded and shared, you can read the slide later. I will not spend too much time, but I have listed for the benefit that all these things we are not doing in simulation when we simulate for sheet forming. Whereas press makers, if you see, they are doing simulation, and it looks pretty bad actually if you see how it is flexing, deflecting, deviating from ideal. Okay. Now, under this scenario with bulk force where you are applying 2000 ton and 1000 ton, okay, it's a brutal force. Now, what kind of precision do we expect? And we are not doing this simulation for stamping dies. We are not doing this simulation for other things. So, piecemeal we are doing. That's a problem. And then precision does not depend only on the press. It does not depend only on the equipment. It depends on tools. It depends on fixtures. It depends on everything. For example, you can have a case. You have a press bed. You have a die which is very rigid, designed to be very sturdy. Now, what will happen that when 2000 ton comes, the bed will flex and there will be gap underneath the die. Okay, there will be a gap underneath the die. So that's not a comforting situation. Another extreme case, when this is made very flimsy, then the die is made flimsy so that it will deflect along with the table. Now one has to argue which is better. When the die is getting distorted, that is better, or when the die is not getting distorted, but it is floating on the table, which is better. So now that again, I leave for manufacturing people to go into detail and figure out. But then these are the challenges in precision when it comes to stamping. Okay. So large size dies, it is a common knowledge that they are almost never first shot okay upon manufacturing, because the machines where the dies are machined, they are breathing around 0.5 millimeter during day to night, during 24 hours. And the castings are getting machined for a long time, continuously for more than 24 hours at a stretch. And for making a good die, a precision die, you require matching of upper and lower die in a precision of 10 to 20 micron. Okay. Now, if the machine is breathing, if the casting itself is breathing by 0.5 mm, where is 10 micron? Where will you ever get it? So you don't get it. So then you have to do haath ki safai, handwork, and match the upper die with lower die. Arbitrarily, you assume that upper is always right, upper wala is always correct, and you suit the lower die to upper die blindly, and that's how the thing goes on. Okay, but 10 micron is a far cry. And the machines also, because of several reasons, okay, these two pillars will expand. Suppose temperature shoots up by 10 degrees. Okay, the steel will expand by 10 micron per meter per degree. Okay, now, okay, the columns will become taller, spindle will become longer. What happens when the cross beam will become longer? It will become like a banana. It will become like a banana, as shown here. Plus, there are guiding clearances, there are LM guideways, there are bearings. Each thing which is having a running fit will have a clearance of at least 7 to 10 micron, which will get magnified with the large cantilever. Okay. So, whereas your positional accuracy, positional precision is 0.5 mm, you are expecting 10 micron out of it. So, that's you are never going to get it basically. So, that's a challenge. Coming to the presses, now this is a typical press. Now, press is made of three major parts. So, there is a crown, there are four uprights, and there is a base, and the three are tied together with four tie rods at the four corners. Okay, because suppose you are applying 1,000-ton force downward, will the crown not get lifted? Yes, it will get lifted because crown weighs only about 80 tons. Okay, if you are pressing 1,000 ton, the reaction has to go somewhere. So reaction goes in stretching the four tie rods. So each tie rod will have 250 ton trying to pull it. Okay, that is physics. That will happen. And the way the presses are designed, at the rated tonnage, the tie rods are supposed to get elongated by 7 millimeter. Now we are talking of micron precision, and this is 7 millimeter of distortion. Okay, it is by design. Yeah. So that's why I say it is very difficult to talk of precision when you talk of stamping dies, because it is a brute force method. It is brutal. And we are not having air conditioned room for presses. Obviously, the room temperature is fluctuating. Dimensions are very big. Okay. So, plus when the presses get old, the bushes, brass bushes will become oval everywhere. Okay. Linkages may get permanently bent also due to some abuse. Gears will have a play, and suppose there are four parallel paths of gear trains, they may have unequal wear. So in air, the ram may look parallel, but when the force comes from bottom, it will rock, depending on the relative clearances which are there. So again, it's a challenge. And underneath in the bed, there is nothing below the table, so it is free to sag. It has to be like that, because below there is a cushion. So you can't build any support underneath. Okay. So when the full force comes, a table is free to sag. It will sag. It is designed to sag like that. Right. So another aspect is, of course, guiding clearances. We have variety of guidances. 4-point and 8-point guiding puts diagonally, gives put diagonally, or 8 of them put where they can be adjusted individually. Now, again, I leave to the intelligent users to figure out which one is better. Obviously, this one is better, but it's costlier. So precision depends on all these things. Okay. Talking of hydraulic press, you have 4 cylinders at 4 corners. The oil will not flow in the same way in all 4 cylinders, because the oil pump is common. So it will reach first cylinder first, second cylinder second. So the press will come down like a kati patang. It will not come parallelly. And that will happen. That's physics. So you have to have some active parallelism mechanism in order to incorporate precision. Something like a mechanical torsion bar, probably, or something like a hydraulic torsion bar, where you have cross-connected cylinder and you try to correct the imbalance of forces coming from the die and imbalance of forces coming through the hydraulics actively. Okay. So these are the things which something like this. This is called a hydraulic torsion bar. So these things you have to incorporate in the press in order to ensure precision. Okay. Coming to laser beam, yes, laser beam is supposed to be much more precise for cutting. You can compare, this is a curve If you have plasma cutting, flame cutting, water jet cutting, laser cutting. So laser cutting is obviously much more precise because it is adaptive. You can adapt the laser beam power, the beam mode, the focus. It is like a sharper knife. It produces heat in a very localized manner, so there is minimal damage, there is a lesser thermal effect. And so we have applications like cutting stents from 20 micron thin stainless steel tube, which can only be done with laser cutting. Thicker plate one can cut in n number of ways. All these ways I have shown here. Okay, and other ways are much cheaper than laser cutting probably. But here there is no other way to do it. Okay, so where precision is required, there laser beam is the only thing which one can remember. Okay, so it's a debate that whether laser should be used for thicker or thinner sheets. Okay, according to me, it should be used for thinner sheets because there is no other way for cutting thinner sheets. Talking of welding, again the width of weld and heat affected zone for laser beam welding is much smaller than other welding, including electron beam welding. Now, why electron beam welding? Because we say light microscope is restricted because by a wavelength of light. Electron is much smaller, therefore it has much sharper resolution. It has much bigger magnification. But EB is less precise than laser because electrons will repel each other. So there will be beam divergence, which laser will not have. So this is laser cutting. When you talk of cutting thicker plates, the problem is all this finish that you can see, jagged edges, beveling, variable curve, heat affected zone. All these things are the measure of precision in laser cutting. Okay, so you have to inspect, you have to put a camera, probably you inspect and you actively compensate the deterioration of cut edges. Okay, and you try to improve the situation of precision by some adaptive means. Okay, so with physics there is a limit of precision, but when you put adaptive means, you can go beyond physics and achieve precision. So that is what is being done in case of laser beam. Okay, further you can have beam power mode, depth of focus, covering gas, etc., adaptively varied in order to have uniformity in cutting. You can use circular polarization of beam. If it is linear polarization, in one direction cutting will be good, in other direction it will be jagged edge. Okay, so circular polarization is must. If you are cutting a square at the corners, you have to reduce the power, otherwise corner will overburn. You have to have auto adjustment of power mode focus, so this adaptive part is there. And instead of using larger beam to have bigger plate cut with a thicker curve, you can use a smaller, sharper knife and draw circles, while progressive circles while cutting. Now that is called as locus cutting. Okay, so you preserve much better quality of cut edges. Okay, with much sharper knife, but the mode of cutting is different. Maybe you are spending more time, you are sacrificing on a productivity a little bit, but the quality and precision is maintained. So sometimes precision comes at the cost of productivity. That's the other part. Another, with laser beam, you can enhance it by having what is called a laser jet. You have a water jet and inside you have laser. So with multiple reflection, the laser beam comes out without any divergence, and you can get a much more accurate. Sorry, video is there, but I will jump the video.
Are absolutely parallel due to the perfect geometry of the laser beam, which is defined by the water jet. The water cools the workpiece and prevents the heat damage typically resulting from laser cutting. Melted particles are cleaned away. The workpiece remains free of burrs and debris.
So, sorry, I'm not showing you full movie. I'm just showing you a glimpse, jhalak dikhla ja types. So this is laser jet. So you can kill many of the less precise features of the laser beam by having combination of water jet with laser. Okay, so that's the technology, and the precision gets a big boost because all these divergences, beveling, heat damage, etc., can be prevented once you have laser microjet. And so it is used for having precision, very small holes in turbine blades. Okay, so where precision delivers. Now another aspect where you use laser beam is surface modification. You can instead of honing, you melt 2 micron depth with laser. Okay, just 2 micron. So that is a substitute of honing. Now honing is said to be the most precise machining process by far. Okay, honing and lapping are by far super finishing methods. Yeah. So honing is most precise method, but there also you use laser beam, and instead of producing surfaces like this one, honed surfaces, you get melted surfaces with some grooves still remaining, which can still hold some lubricant. That's the idea of having grooves. That's the idea of not mirror finishing the surfaces and leaving some grooves for the oil retention. So that property is still there. Now, if you laser hone the automotive cylinder, the efficiency goes up because the leakage is reduced through these channels which are there. Okay, through the piston rings. Okay, so now these are the various laser cutting various laser beam areas. Different beam size, different beam quality is used for different things. Okay, for different application. Now, one of the application is laser hardening. So, you use the beam, run over the die and mold surface and harden it without distorting the die and mold. The challenge is, however, the challenge is that this is a die. Now, suppose you were to harden with induction hardening or flame hardening. Okay, you will heat and quench the surface. The mass associated is uneven because somewhere you have ribs, somewhere you don't have ribs. Okay, so how will you get uniform hardness? And if you don't get uniform hardness, you can see the hardness in the sheet part which you hit. Okay, so therefore, you use laser with adaptive control. Okay, with adaptive control, this is just showing the laser hardening. Okay, so it is like running brush on the surface so that you produce hardness band. Okay, but instead of running it indiscriminately, you have something called as a radiation pyrometer, or you have thermography nowadays, which is non-contact monitoring of surface temperature. So if there is a rib underneath, you can reduce the laser power at that part locally while scanning. Okay, now that is the adaptive part of precision. Okay, and you can also have different kind of beam mode controlled automatically, switched between this and this and this to have a good finishing of edges, sharp edges, good surfaces, good depth of hardness, and so on. Okay. Now, if somebody is doing welding, for example, normally we say for precision, you have to have a good workpiece. Now, if workpiece is having variability, how do you have a precision? Okay. You can have adaptive control like this one, for example. So, basically, you are sensing the seam. The seam may be, sorry, I'll skip the video and show you this. Suppose you have a job where the seam is irregular and you don't know the seam. You have something like a barcode reader which reads the exact location of seam and it diverts the laser beam there while welding. So, irrespective of a big variability in the incoming job, you can still have precision through the process. Okay. So, finally, my question is laser beam more precision than a stamping press for mass production? No. In terms of process capability, CP/CPK, sigma level, stamping press is anytime better than laser. Okay, so it's a contradiction. But depending on situation, the actual findings vary when you talk of precision, because precision has multiple dimensions, as I said. Thanks for your kind attention, and that's all from me.